All right, I think
recording in progress.
All right, welcome to this plenary session. It's a great pleasure and honor to chair this session. My name is Reinhard Kienberger from Technical University Munich, and we have two speakers today, Carlos Hernandez Garcia and Charles Mukamil. And we start with Carlos Hernandez Garcia. He's associate professor at Universidad de Salamanca in Spain. He received his PhD in 2013 at this university. Then he was a postdoc with the Marie Curie Fellowship at Chile, University of Colorado, for 2 years. And now he's a principal investigator of an ERC starting grant about structured attosecond pulses for ultrafast nanoscience. His interests cover nonlinear optics and ultrafast phenomena, focusing on the ability to generate structured laser pulses for the application in attoscience. And he's recipient of the EPS Quantum Electronics and Optics Division Fresnel Prize in 2019 and the Young Scientists Prize IUPAP in Atomic, Molecular and Optical Physics in 2021. So welcome, Carlos. Thanks for giving your talk on structured light topology in ultrafast nonlinear optics. The floor is yours.
Okay, so thank you very much, Reinhard, for your really nice introduction, and thank you for the invitation and the organizers of this wonderful conference. I have to admit that my first conference ever was a laser physics back in 2009 in Barcelona, in Spain. And it really inspired me. So I'm really happy that now I have the opportunity to give a plenary talk in laser physics. And I really want to thank the organizers to keep this conference over the years. I think it's really a really nice conference that I'm really proud now of being part of it as a plenary speaker. So thank you, the organizers. Thank you, Reinhard, again. And yeah, try to now have the responsibility after all these years to try to enjoy you during this really exciting topic of structured light. Okay, so today I'll be talking about the work we've been developing over the last, let's say, more or less a decade, about structuring light in the ultrafast, and seeing somehow this we can tailor, observe, and control processor with structured light thanks to nonlinear optics. So first of all, let me just define for you, or you might be wondering, what do we call by structured light? Yeah. So during the last years, there's been many works, many covers in journals talking about complex light lasers, structured light, twisting light. Okay. And the fact is that we have an amazing tool, which is laser light, that there are a myriad of possibilities nowadays to structured light. Starting for the plane wave description, we all know from basis optics, we can really tailor the amplitude, time, space, polarization, phase, and frequency of light, giving rise to many different kinds of light that we may call structured light, okay? But for me, I will call about structured light in laser beams that are spatially structured in their amplitude, phase, and or polarization. Okay, so those are the three different properties that nowadays we can really tailor in space. And for me, that's really the definition of what we call nowadays structured light. So let me remind you what are the basic properties of structured light. And I can tell you that these different spatial distributions of intensity, amplitude, phase, and polarization can be very well described through the angular momentum of light. So we can remind that we have two kinds of angular momentum. We have first the spin angular momentum, which is no more than the polarization of light. Yeah, we have right circularly polarized, spin 1, left circular polarized, spin -1, and the combination of the two of them, we have linear polarized. Nowadays, by combining many different structures of different polarizations and combining polarization and frequency, we can generate, for example, what are called the bicircular fields, which is no more than the combination of two beams with different frequency, in this case, omega and 2 omega, and in this case, which are counter-rotating. We can really tailor an electric field in this way, for example, and there are many, many ways, as we'll see. Also, nowadays, we can construct three-dimensional light fields, like, for example, this chiral light, yeah? We add a small component of the longitudinal component, we can define these really exciting electric fields, in which the group of David Ayuso, with Olga Smirnova and Misha Ivanov, they've done a great job in generating and controlling these light fields. Okay, so we have the spin angular momentum related to polarization, but we also have another kind of angular momentum, which is orbital angular momentum. And orbital angular momentum is a macroscopic property, which is related on how the phase distribution of the beam as it propagates. Yeah. So, for example, here we have a beam with no orbital angular momentum, which is a standard Gaussian beam, standard Gaussian intensity, and flat phase profile if we are focused. Okay, but if we add a spatial distribution of the phase, for example, in this case, we add a 2 pi phase shift variation along the azimuthal coordinate. Okay, then we have a beam carrying orbital angular momentum. Those beams, you can see very easily that at the very center, there is a singularity, a phase singularity, so that the intensity has this well-known profile, well-known donut profile, okay? And depending on how many 2 pi phase shifts we have along the azimuthal coordinate, we have different kinds of orbital momentum, which are defined through the topological charts, okay? One 2 pi phase jump L equal 1, 2 pi phase jumps, this is L equal 2, okay? We have these helical phase forms that are defined with this topological chart. This is the number with the proportionality to the azimuthal coordinate. Okay, how can we relate these two different properties of light, the spin angular momentum and orbital angular momentum? Of course, we can have any kind of angular momentum, of beams with orbital angular momentum. Those are also known as vortices, okay? But their polarization state can be any polarization state. So, for example, if we plot these little green arrows that we have over here, this will be a beam, a vortex beam, carrying orbital angular momentum, which is linearly polarized. Okay, but these beams, in principle, those are two separate properties, and these beams can carry any polarization state. Okay, so for example, we have spin angular momentum, orbital angular momentum, and we can combine them. And we can create really fancy beams like these vector beams. Okay, vector beam is no more than a beam whose polarization state changes along the transverse dimension. In this case, it's not the polarization state, it's the tilt angle of a linearly polarized beam. And we can create such a beam, a radially polarized beam, for example. And these beams, they can be interpreted very nicely as a superposition of two beams carrying orbital angular momentum. In fact, this beam is no more than the superposition of a left circularly polarized beam and a right circularly polarized beam carrying orbital angular momentum -1 and 1. And this decomposition will be really useful to understand the conversion laws that we have in nonlinear optics for these beams, as I will let you know. Okay, we have these beams, and these beams sometimes they can be somehow difficult to characterize. So we need to really define topological properties of these beams to have them well defined and to see how they are scaling and in different properties, in different interaction regimes. Okay. So we can define two, let's say, characteristic light topologies, which is, for example, the topological charge. I already defined it. The topological charge is no more than this integral that we have over here, which is basically the phase along the integral of the phase along the azimuthal coordinate that we have over here. But for example, if we would like to characterize the topology of a vector beam, yeah, such as this one over here, we can define another quantity, another index, which is the Poincare index, which is this quantity that we have over here. Now we have the integral, not of the phase, but of the tilt angle. You see here, the tilt angle at any position in a space. We can perform the integral about how this tilt angle is changing along this line, and we can define thus the Poincare index. So, for example, this beam, which is a radially polarized beam, we have a Poincare index of 1, one full rotation of the tilt angle along the azimuth. And we can also think about this other beam, okay, in which we have two full rotations, and then the Poincaré index is equal to 2, okay? So these are more or less the beams that nowadays are really interesting, and I will let you know why. For example, one brief example that I would like to know is that vector beams nowadays, azimuthally polarized vector beams, they can exhibit a strong magnetic field where we have the singularity of the electric field. And this is very exciting because nowadays we can think that we can tailor and space different regions in which we have an electric field and a region in which we have an isolated magnetic field. And we can think and we can start doing research for the first time about a nonlinear interaction in which we only have a magnetic field without the presence of electric field. And this is really exciting. There's been different proposals to do this, and there is, for example, the work of Paul Corkum that they have demonstrated the generation of these beams and the generation of this particular ultra-intense magnetic fields associated to these structure beams. Okay, so the two main goals of this field, let's put it this way, are two. So we have first the upconversion of a structure light into the ultra-fast and soft X-ray regime. Yeah, this is very exciting for different interactions and looking for properties, for example, in the edges of magnetic materials, the absorption edges of magnetic materials. But these beams also, they can be used to extract dynamics information from their interaction with matter. So on the one hand, we have the generation of these beams in this ultra-fast high-frequency regime, and their interaction with different materials. For the first part, the challenge here is that we can tailor the spin angular momentum and the orbital angular momentum in the infrared or visible regime with, let's say, standard wave plates, yeah, or standard spatial light modulators. Yeah, with these devices, we can routinely generate beams, structure beams with tailored polarization and tailored orbital angular momentum in the femtosecond infrared visible regimes. However, these devices are very inefficient in the extreme ultraviolet and X-rays. So one of the solutions that we came out is, okay, we can try to convert these beams from the infrared towards the extreme ultraviolet or close to the soft X-rays, thanks to the process of harmonic generation. And this is what we've been working during the last decade. And we've been working hard because this conversion is not trivial. Harmonic generation is a highly nonlinear process, and this conversion was far from trivial. And I'll let you know in this talk about it. And on the second part, as I told you, we really want, and we really have now the ability to extract new dynamic information from the interaction of the structure light with matter. As I will show you, by looking at the topological properties of the beams that are emitted after interaction with different materials, we can really characterize new properties or different properties of their materials. Actually, in the process of harmonic generation, we can really learn things about higher-order harmonics and about the nonlinear process of higher-order harmonics just by looking at how the properties of the structure beams are upconverted into higher-order harmonics. Okay, so I will split this talk in three different parts. The first two parts are related to the generation of these beams in the ultrafast nonlinear regime. The last part is about the characterization of electrodynamic properties thanks to the use of this beam. So let's start. I will tell you first how to generate circular polarized rosette pulses, and then how to imprint orbital angular momentum in the high frequency regime thanks to high harmonic generation. So the thing is, in high harmonic generation, as most of you know, we have a linearly polarized infrared driver, typically, yeah, which is focused into a gas jet, and the high nonlinear interaction in each one of the atoms, which is depicted in this movie that we have here. The high nonlinear interaction is really doing this nonlinear wave packet dynamics in the vicinity of the atom that can be characterized to the well-known three-step model, ionization, acceleration, and then recombination back to the parent atom, leads to the emission of high-frequency harmonics. Yeah, and these harmonics in the time domain, they are emitted as trains of arrow-sequences. Okay, so these dynamics are along the direction of the polarization of the electric field, and as a result, the harmonics are generated linearly polarized. What if we would like now to generate harmonics with a polarization which is different from linear? So the first approach would be, okay, if we drive the process with the laser, which instead of linearly polarized is circularly polarized, we might be able to generate circularly polarized harmonics. However, this is not the case. If we derive harmonics with a circularly polarized driver, we end up with no harmonics. And this can be easily understood because if we look at the wave packet dynamics, we have this ionization, acceleration in the continuum, but due to the circularly polarized behavior of the laser field, the wave packet is really shifted away from the parent ion, and it does never recollide back with the parent ion. So then the efficiency of harmonics drops drastically with the electricity. This was well known from the early 90s, as you can see here. And there have been few techniques until the last decade where different techniques have appeared to solve this problem and to generate harmonics with circular polarization. And one of the most exciting techniques you can imagine, and the way I like to explain this is, okay, we have this shifting of the wave packet away from the parent ion. If we use a circularly polarized driver, let's say a right circularly polarized driver, okay, maybe we can use another beam which has left circularly polarization, so we can somehow lift back the wave packet towards the parent ion. Yeah, but if we have circularly polarized plus left circularly polarized, same wavelength, we end up with linearly polarized. So we are, in this case, we have not gained anything. Yeah. However, what happens if we drive this scheme with two different frequencies? Yeah, and this is what you have here. If we have, for example, omega 2 omega 800 and 400, we have this bicircular field. I already explained before. Yeah, this is how the field looks like. This threefold field. And now, if we look at the wave packet dynamics, they do recollide. Yeah, and this is really nice. Now we have recollision, and as a result, we have the emission of a spectrum that has these peculiar properties. The spectrum is composed of higher harmonics, pairs of harmonics, one harmonic missing, a pair of harmonics, one harmonic missing, and within this pair, the harmonics that have opposite circular polarization, opposite handedness, right, left, right. Okay. I will not go into the details of why we have this spectrum. This is due to parity conservation and spin angular momentum conservation in the process. This technique, actually, it was predicted back in the 90s. There were these really nice papers in the late 90s where they predicted this technique, the use of the bicircular field, and they predicted theoretically how we can generate these harmonic combs with pairs of harmonics whose polarization is circular but opposite. But it was not until 2014 when this paper came out from the group of Oren Cohen and Technion, and they actually did the experiment. And as you can see here, at this angle over here, you have these pairs of harmonics that exhibit circular polarization, and for the first time, circularly polarized harmonics were generated. Okay, and thanks to also to this paper, the angular momentum conservation was explained to obtain all these different channels we have over. Since then, there's been plenty of works that have really, tailored this approach to try to generate these circularly polarized harmonics using this scheme, and many more that I'm really missing here. Forgive me if I'm missing any relevant work in this field, but it's been really an exciting field because for the first time we were able to generate circularly polarized harmonics. Okay, but one of the great things of harmonic generation is not just the spectral domain, it's going into the temporal domain. Okay, but in this case, how are the arrow-second pulses emitted in time? If we look here in the spectrum, as I said, we have pairs of harmonic with opposite handedness. So it is not trivial to think if you perform the Fourier transform in this spectrum, how is the polarization of the Arrowsec pulses? And here you have the answer, actually. It's a kind of very complex attosecond pulse train because each pulse presents linear polarization, but whose tilt angle or polarization direction is rotated 120 degrees from pulse to pulse. Yeah. So, okay, this is nice. We have this train of attosecond pulses, but however, within this technique, we cannot generate circularly polarized attosecond pulses. Yeah, that can be really interesting for certain applications. So there's been works where they've tried more or less by using this technique to enhance and suppress some of the different harmonics, some of the different families of circular and circular. But I think that the technique that really nailed it and was able to generate circularly polarized harmonics was this other technique, really nice technique that was developed by proposed by Chip Durfee at GIVA in collaboration with a group of Henry Captain and Margaret Main. And this is a different technique that is based in the macroscopic picture. Now here you can think if you have two non-collinear laser beams, yeah, but in this case, same color, but different handedness, right circularly polarized and left circularly polarized. If we look at how is the electric field distribution at the target, at the gas that typically we have at the harmonic generation, we have this field distribution, which means that we have linearly polarized electric field, but that is rotating along the transverse plane, as you can see over here. Then, locally, we are fine. Locally, we have efficient generation of harmonics because the wave packet dynamics will follow a linearly polarized field. So then this is great. But what happens here is that once we've generated harmonics with this polarization distribution, if we go into the far field, we will generate two beams of harmonic, one which is right circularly polarized and the other which is left circularly polarized. In other words, there will be two positions in the far field in which the delay between these emission from different places along this axis will end up with the right circular or left circular polarization. And this you can see it here. This is the photon energy, harmonic, different harmonics. This is the divergence angle. And you can see how we have these two families of right circularly polarized harmonics and left circularly polarized harmonics. Now, if we, for example, look at some divergence angle, we will have the overlapping of different harmonics, then we really have circularly polarized attosecond pulses. Yeah, as you can see here. So these are the results, for example, of the experiments performed in the group of Min and Chen at Taiwan, where they were really able to measure the circularly polarized attosecond pulses, implementing a gating technique to obtain an isolated attosecond pulse, and also being able to tailor the electricity of these pulses through the electricity of the driving field. Okay, and also thanks, for example, to one of the nice things that came out of this technique is that by characterizing the polarization of the attosecond pulses of the higher order harmonics, what is called this ellipsometry technique, by characterizing these properties, one can extract information of the higher order harmonic generation process of the quantum wave packet dynamics in the gas cell. This is really, really nice. Okay, so since these are two different works, but there's been different works nowadays that were able to generate elliptically polarized harmonics or nearly circularly polarized harmonics by doing harmonics in anisotropic media, molecules or solids. They were able to generate elliptically polarized harmonics, not circularly polarized, though, using two color linearly polarized drivers or combining two harmonic sources with orthogonal polarization and then adding them up in these nice works over here. But as you can see, in all these works, the recipe was kind of similar. Let's change our driving field to try to tailor the properties of the generated harmonics or attosecond pulses. So this has been also the recipe we follow for imprinting orbital angular momentum in the EUV thanks to the process of high harmonic generation. And now again, so how can we imprint orbital angular momentum in these attosecond pulses of high order harmonics? So in other words, how can we generate vortices in the ultra-fast, extreme ultra-fast attosecond regime? So again, we start from harmonic generation, and as we did with spin angular momentum, we can now think of having an infrared vortex driver. Yeah, which has this spatial structure, intensity and phase. And here, the first thing that was not that obvious is, okay, if we shine harmonic generation with this driver, how is the topological chart of the different harmonics? And this was, as I said, this was not easy because there was a first experiment whose results were controversial and were going against orbital angular momentum conservation. But luckily, we did some theoretical research here, and then that was then experimentally confirmed afterwards, that show that orbital angular momentum is conserved in harmonic generation. That means that the topological charge of the different harmonics is Q times the topological charge of the driver, where Q is the harmonic order. This can be easily understood, even from the photon picture. Yeah, imagine you are generating the 17th harmonic, so you are absorbing 17 infrared photons with L=1, yeah, and then you are emitting an extreme ultraviolet photon through orbital angular momentum conservation. The OAM of the emitted photon has to follow this very simple rule. So these are the results from our simulations. Here you can see the intensity profile and phase profile of two harmonics, the 17th and the 23rd. You have this very nice donut profile in the intensity, that you can see. And if we look in the phase, you can count here different 2π phase jumps. And if you count carefully, or you can believe me, here you have 17 phase jumps, and here you have 23 phase jumps. A clever way of counting is performing the azimuthal Fourier transform over here. And this is what these plots reflect. Here you can see the result of 17 and 23 for the topological charge following this law as we predicted. How are these harmonics emitted in time? How are the attosecond pulses emitted? This is again not trivial. We have different harmonics with different orbital angular momentum, and the result, and here you have to believe me, again, is this really nice helical attosecond pulse structure that was also denoted as a light spring in the attosecond. Okay, so thanks to harmonic generation, we can really generate harmonics with this high topological charge. What is the highest topological charge generated up to date? Thanks to harmonic generation, we've been able to generate up to 100 topological charge. So these are results from the group of Sophie Cazamias in Paris-Saclay in collaboration with our group in Salamanca. We were able to generate harmonics. For example, in this case is the 25th harmonic of a driver with L=4. 4 times 25 is to avoid front with almost 100 2-phase shifts without topological charge close to 100. These are the different experimental results that confirmed this orbital angular momentum conservation in the group of Corkum through interferometry, in the group of Sophie Cazamias in Paris-Saclay through wavefront sensoring, or in the group of Thierry Gouchon in Paris-Saclay through rabbit measurements, where they were able also to characterize this light spring, this attosecond light spring. Okay, so at this point, we were digging a little bit into this, and we decided, okay, what happens now if we derive harmonics instead of one OAM beam with two OAM beams with different topological charts? And this led to a very exciting result that led to something which was really, really fun for us to work, which is now the harmonics, they do not possess just one orbital angular momentum contribution, they possess several orbital angular momentum contributions. And this can be well understood also from the photon picture, because we know, again, we try to generate the 17th harmonic. We have to absorb 17 harmonics, but we can pick from L=1 or L=2. Depending how many photons we pick from each one of the drivers, through orbital angular momentum conservation, we will have different channels. Yeah, and this was very nice, and this is how the 17 harmonic look like, the intensity profile, this crescent shape. And if we look now at the phase profile, okay, now it's more complicated to count 2π phase jumps over here, yeah? However, thanks to the azimuthal Fourier transform, we can really see this spreading in the orbital angular momentum contribution that we have in these beams over here. Okay, so the next thing we did is now what happens if we perform a time delay between these two beams, okay? And this is what's really, really fun and really interesting. Here, this is you can think as this is the driving pulse with, first we have the L=1 in blue, and then we have the L=2 in red. And if we follow the orbital angular momentum conservation, and for example, here we look at the 11th harmonic order, at the front part of the pulse, we will generate L equal 11, and at the rear part of the pulse, we will generate L equal 22, 2 times 11. But what happens in the middle? In the middle, what will happen is, depending on the weight between the two different pulses, we will go through all OAM content from 11 all the way to 22. Yeah, and you can see this in this movie. This is a movie. This is the phase profile, intensity profile, and orbital angular momentum content. Here at the front part of the pulse. Now we start and we go towards the rear part of the pulse, and you can see how the OAM is going all the way from 11 towards 22. And this is, for the first time, we were able to generate a laser pulse whose orbital angular momentum contribution is changing along time. Yeah, this is what we denoted in analogy with mechanics. A variation of time of the orbital angular momentum is the torque. So we denoted this property as the self-torque because it's a torque that is not a torque that is exerted by the laser beam into a particle. No, it's a torque that is carried by the laser beam itself. And you can see here this analogy. And now you can think, okay, these are quite complicated pulses, Carlos, that we are doing with this structure. Like, how can we measure this in the lab? How can we generate them, and how can we measure them? It's really difficult now. It's already difficult to measure such a waveform that has this high topological charge, but now it's really changing quickly in the time domain. We obtain the recipe to do a very quick and very easy measurement of this property. And the fact is that we really found out that a variation in time of the orbital angular momentum is analogy. It's analogy in the chirp along the azimuthal coordinate. Yeah, a variation of the orbital angular momentum in time leads to a beam with what we call azimuthal chirp. And an azimuthal chirp is easy to characterize in the lab, yeah, because you just look at your spectrum, the intensity, and you can see how the frequency of your beam is changing along the azimuthal coordinate. And this is related through what we see over here. If we look at the intensity, at the local intensity at different positions in space, which is no more than the derivative of the phase of the harmonic in time, we have the instantaneous frequency, the frequency of the harmonic, but thanks to this term that we have in the beams with orbital angular momentum, L times V, you can see over here, if we perform the derivative in time now, we have a new term in the frequency that changes along the azimuth according to the variation of orbital angular momentum, which is no more than the torque. Okay, and you can see it here. So thanks to this property, the group of Henry Captain and Margaret Moorman, led by Kevin Dorney, were able to perform the experiments at the University of Colorado, and they really followed our predictions in Salamanca performed by Laura Rego. So you can see here the really nice agreement of the self-torque exerted for different harmonic orders. So these are some examples of all the different possibilities we have nowadays to really tailor the angular momentum of light in the extreme ultraviolet regime. Thanks to harmonic generation, we not only did circularly polarized harmonics and orbital angular momentum vortex beams, we also conjugated the two properties, and we were able to generate, for example, circularly polarized vortices, yeah, that were really nicely explained by the theory of Emilio Pesanti in terms of the torus, not angular momentum. We were able also to predict and generate in collaboration with the group of Thierry Rouchon, beams with half-integral orbital angular momentum. And we can also, for example, predict the generation of arrow-second pulses whose polarization state changes from pulse to pulse thanks to orbital angular momentum. Also, we've done some works in generating what we call vector vortex beams, which are a combination of vector beams with orbital angular momentum. Okay, so one of the really nice things we did also is, okay, can we really change properties of the harmonics thanks to orbital angular momentum? And one of the most fundamental properties of harmonics is the generation of odd-order harmonics. The lane space in between harmonics is 2 omega. Yeah. So, and this is related because you have 2 events per cycle. Yeah, our second pulse has 2 events per cycle. It leads to a comb with a line spacing of 2 omega. If you would like to, for example, generate a combo of harmonics with a line spacing of 10 omega, this would require 10 events per cycle, which seems difficult from the single atom picture of harmonic generation to have 10 attosecond pulses per cycle. Yeah, how can we do this? We can do it. And looking at the macroscopic scale. And if we look at the macroscopic scale, for example, we can tailor a driving field, such as this field. You have 5 different lobes with 5 different spatial phases. Yeah, and what can happen is that you can coherently add the emission of these 5 different lobes and look at the emission on axis. What you have is a time delay emission, and this emission from the 5 lobes that is time delayed leads, in this case, to these 10 events per cycle. And if you look into the spectral domain, in fact, you have this control over the line spacing. Where does orbital angular momentum enter the game here? Is because we can generate these beams just by combining 2 beams with different orbital angular momentum, and in this case, with opposite charges. In this case, L equal 2 and L equals -3, you have this beam. And this we can do, by changing the OAM content of these 2 beams, we can really tailor and control the line spacing of the harmonics. This was corroborated experimentally in the lab of Henry Captain and Margaret Lane in the experiments done by Nathan Brooks and Quinn Nguyen, and in comparison also with the theory of Laura Rego. You can see here the theory and here is the experiment. And if we look at the emission on axis, you can see here that some harmonics are suppressed, in this case driven by L equal 1 and L equal -2. We expected a line spacing of 6 omega 0, and here you can see how, in fact, you have this line spacing of 6 omega 0. So thanks to orbital angular momentum, we were able also to control the frequency content in terms of the line spacing between the harmonics in harmonic generation. Okay, I will go to the last part of my talk because I'm a little bit running a little bit of time. So one of the proposals we have now is to perform what we call light topology spectroscopy, which is to use topology as an additional parameter to a standard spectroscopy to retrieve information of the interaction between our laser field and the material in which we're interacting. And for this, solids are very interesting. Yeah. So recently, not recently, already in the last decade, there's been a lot of work in the field of harmonic generation in solids. And in this field, we can basically replace the standard 3-step model by now looking into the reciprocal space, looking in the band structure of our solid, and in the reciprocal space, we can understand the 3-step model as an ionization or a promotion of an electron from the valence band to the conduction band, acceleration in the conduction band, okay, and then recombination, which is a recombination between the electron and the hole, and this will be the third step, and this recombination will lead to the generation of high-frequency radiation. So the questions that we had here is, okay, can we really learn and control the dynamics in solids if interrogated by structure light? Yeah, and also can we tailor these structure pulses with solids, or even can we characterize more complex solid structures such as polycrystal or heterostructures? And the answer is that here, structure light plays a fundamental role to answer these questions. It was shown already some years ago, back in 2019, but for example, OM is conserved in solids. This was a work done in the group of Ahmed Merji by David Gautier, that they observed that if we shine a semiconductor, the OAM of the crystal is preserved. Okay, this was a nice work, but we think it's more interesting not looking at beam with orbital angular momentum, just by looking at beam with different polarization states. Why? Because solids, they present an anisotropic response. In contrast to atoms that are isotropic, in solids, the response is anisotropic. Both the intensity, phase, and polarization state of the different harmonics depend, for example, of the tilt angle of the linearly polarized driver that you're using to shine higher harmonics. So we did some simulations in Salamanca using graphene, one of the most basic 2D materials. Why graphene? Because we can exclude longitudinal propagation, okay? the dynamics will not be affected by longitudinal propagation. And we have this really nice dynamics of harmonic generation through the direct points. Okay, the excitation is really localized through the direct points. Graphene exhibits a high anisotropic response. So, for example, here you have the harmonic intensity for different intensities versus the tilt angle of the driving field and versus the geometry of the lattice. And what we thought, okay, what happens if we now derive harmonics with a beam whose tilt angle is changing in space? For example, is azimuthally or radially polarized laser. So there were works in gases, in isotropic gases, and for example, we did an experiment back in 2017 in Salamanca, in which we saw that as gases are isotropic, the profile of a radially polarized laser beam is preserved in the harmonics. So it's directly imprinted into the harmonics. A way to characterize this, okay, let's try to look at the topological indices, at the topological parameters. So a vector beam, a radially polarized vector beam as this, as I said at the very beginning, it can be composed of two beams with opposite topological charge, -1 and 1, left and right circularly polarized. If we go to the higher order harmonics, we can see that, in fact, in the higher order harmonics, the topological charge is preserved, and we have radially polarized harmonics, thanks to the simultaneous conservation of spin and angular momentum. And if we look at the Poincare index, this Poincare index that takes into account how the tilt angle is varying along the azimuthal axis, this Poincare index is preserved. However, what we thought and we saw it was really interesting is that now if we do the same procedure in solids, in this case in a graphene sheet, we see that now the Poincare index is anymore preserved, and the structure, this intensity and phase spatial structure is much more complex, is much more rich compared to that in anisotropic gas such as argon. Actually, if we look at the orbital angular momentum contribution of the left circular and right circular components, you can see that they are not anymore -1 and 1 as in argon. They have new orbital angular momentum contributions. Okay, and here I'm running out of time, and here I just wanted to give the message that by looking at these orbital angular momentum contributions, by looking at the topology properties of the higher order harmonics, we can extract information of the nonlinear response of the target, thanks to the use of these structure beams. I will just go to this part over here. And the idea is that if we are able to look into the far field of these harmonics by measuring, for example, the position and the radius of the different topological structures that we have there, for example, here different topological vortices that we have over here, we can really extract the nonlinear susceptibility of the solid target that is used over there. And we think that this is really powerful because now we can add, on top of the standard spectroscopy techniques, we can add topology as a new parameter to take into account that gives us additional information that, for example, to characterize polycrystals or retrostructure, it will be really, really interesting. Okay, so this ends up to the conclusions that I wanted to share with you, that nowadays we can generate these structured light beams in the ultra-fast, extreme ultraviolet regime, thanks to harmonic generation. And we really believe that this topological spectroscopy is a powerful tool that we can add nowadays when we are interacting with crystals or solid systems. Let me thank all the people in our group in Salamanca, and especially the people that is involved in the theory of aerosecond science. A lot of credit to Ana García Cabrera for the work that's presented here, Alba de las Heras, and Rodrigo Martín Hernández, also José Miguel Pablos, and my colleagues Luis Plaja and Julio San Román. Also, let me thank different collaborators that I've mentioned already along the talk. And that's all from my side. Thank you very much.
Thank you very much, Carlos, for this really wonderful talk. It was really fascinating to see what can be achieved here. And this is really a great success that I can follow here. I see the first question by Barry Walker. Barry, go ahead.
Carlos, that's a beautiful talk. Hello. and I'm going to use an analogy here. It was a sweet talk, okay? Very, very nice. But let's talk about the worker bees. The worker bees, what you're doing with these electrons, and you mentioned this at the very beginning, is very impressive because...
What do you mention, the worker bees?
The electron wave functions that are actually doing the work inside the system to generate all these harmonics, right? Okay, so I wonder, I'm just going to predicate this in the following way, because they're doing all the work inside there, right? You're really controlling what the electron wave functions are doing spatially or even locally, right, at the atomic level. I just want to maybe have you looked at the outgoing wave function, and I'll pose this as a simple question. Electrons are very hard to control in the continuum when they're going out. And for example, I can never get them to go exactly where I want them to go. You know what I'm saying? And so is this an approach, a general area where we could say, okay, I have a single electron and I really want to know what it's doing. Can I potentially direct it with this technology into my detector as opposed to just have it go everywhere like it normally does? So anyway, it's just a thought question, but it's a very nice talk. I very much appreciated it.
Thank you, Barry. Yes, a really nice question. I really think that with this three-foil, for example, the three-foil field and all those fields that are combining different polarization states and different frequencies, we can now have access to really control the local wave function of the electrons. It's not as straightforward as you mentioned, yeah. But I really think that we have now access to control really nicely this wave packet. It's not as straightforward, but now you can also think about using a 3-dimension, yeah, with this chiral light. That's really exciting work that we would like also to look into that. Yeah, we have also these two color fields with different amplitude ratios, different frequencies, three-foil in many 2 dimensions, yeah, but in many different ways. But even with the 3rd dimension, we can control that. So I really think that is thanks to these multicolor bicircular fields, we can control as we were not able in the past. But it's difficult, as you mentioned.
Okay, thank you.
Yeah, thank you. I see another question from Ekaterina Orlova.
Hello. Do I understand properly that all those different degrees of freedom of beams are important for multiplexing or in information transmission? And what about detection? Are there problems in fast detecting and and making a differentiation between different these degrees of freedom? How fast and how many detectors you need to detect fast this information?
Yeah, this is really nice. Let me go back to this slide over here. So right up to now, the different methods that have been used to detect the different orbital angular momentum components of this light have been relying, in this case, in interferometry, okay, and in this case in wavefront measurement, wavefront sensing, and also in this case based on RABIT, which is photoelectron ionization. So it is really complicated to measure the wavefront in time for these ultra short arrow-second pulses. Even the standard Reinhardt knows this very well, better than me. Even with no orbital angular momentum with a Gaussian beam, it's really complicated. Thanks to the attosecond stripping techniques, we can nowadays measure this wavefront of the harmonics of the arrow-second pulses. Sorry, with the standard beams. Doing this spatially resolved is really a challenge that we have ahead of us. Doing this in time. These are the techniques that nowadays have been able to characterize the orbital angular momentum of those beams. And the multiplexing the different content of OAM is also a complex nature in this ultra-fast scale. In the infrared domain, I think there are many techniques that they were able to do this really nicely. Okay, this is easy, but in this ultra-fast domain, those are the works that have been developed up to now, and it's not straightforward to resolve in time the OAM of this beam. I don't know if I've answered your question.
Yeah, thank you very much.
All right, thank you very much, Carlos. Since we are a little bit far in time, well, Olga, I can't prohibit you a question. Go ahead.
Well, sorry. Thank you so much, Carlos. Very exciting talk. A lot of possibilities to control properties of light. But my question is, in terms of producing of attosecond pulses in XUV range with the highest intensity to produce circular polarized pulses, what you think is the best way to proceed?
That's a very nice question, because I think this is one of the challenges that we still have in high harmonic generation. Up to now, circularly polarized harmonics, the most efficient way in harmonic generation was by combining this omega and 2 omega field. Okay. However, if you want to extend this to the water window or to the soft X-rays, one of the recipes that we know in harmonic generation is to use longer wavelengths for the driving field, to the mid-infrared. However, this is very tricky because you really need really accurate ellipticity of these drivers up to more than, for example, 99% of circularly polarized if you want to generate circularly polarized harmonics. So it's really sensitive, really sensible. So I think there is a work in the group of Captain Murray that they were able to generate circularly polarized harmonics up to 100 electron volts, 150 electron volts. Above that, we still have to work because it's really sensible, the ellipticity of the harmonics to that of the driver. So this is a challenge that we have to do. Up to now, I would say up to 150 electron volts, the omega 2 omega technique is the best technique to work with that.
Thank you.
All right, thank you very much. Now we proceed to our next speaker, Shaul Mukamel. Shaul, please, could you share your screen while I am introducing you? Shaul Mukamel is a distinguished professor at the University of California in Irvine. He received his PhD from Tel Aviv University, was then a postdoc at MIT and University of California in Berkeley. Then he worked at Rice University, Weizmann Institute, University of Rochester, and finally in Irvine. So he really stayed at very well-known places. He's known for his work in the field of nonlinear optics, especially time domain extensions, which culminated in the widely appreciated book, Principle of Nonlinear Optical Spectroscopy. Shaul received numerous prizes and distinctions, including the Alexander von Humboldt Research Award, the Alice R. Lippincott Award, the Hamburg Prize for Theoretical Physics, the Ahmed Ziveil ACS Award in Ultrafast Science and Technology, the Willis A. E. Lamb Award, William F. Meggers Award in Spectroscopy. So the list is really extremely long. And we are now looking forward to your talk on quantum multidimensional spectroscopies with X-ray light, entangled photons, and in optical cavities. So please share your screen.
Thank you. I'm trying to share the screen. I have a problem here. Let me see if I can fix it. Just a minute. Yeah. I was just a minute. It doesn't. Just a minute. Sorry. Oh, okay. Okay.
Seems good. We at least see a screen. Now we see a talk.
Is it okay?
Yes.
Yes, it's not yet in
the presentation mode.
Yeah, it's not yet in the presentation mode. Now it's in the presentation mode. And maybe there is a message here so that you could click away.
Yes.
Yes, perfect. All right.
All right. Thank you. Thank you. So I would like to tell you about the use of several techniques probe coherences, and I will talk about primarily about using X-ray pulses, but I will also talk about using a quantum light and optical cavities, all geared towards looking at coherences in molecular processes. So these are the key players in this work. Daniel Kiefer was a key person, and Bing Gu and Jeremy Ruxel. All right. So multidimensional spectroscopies have been done starting in NMR in the 50s and going all the way on the frequency scale. And the new frontier is using X-rays to do a multidimensional nonlinear signals. X-rays allows us to use very short pulses, attosecond. Also, they allow us to do core excitations of molecules, and the core excitations are localized on specific atoms. So it gives us a new way of doing nonlinear spectroscopy with temporal, spectral, and spatial resolution. And there is an intensive work effort worldwide to create these X-ray pulses, and I will show you how we can use them to probe coherences. So the idea is to have a combination of optical and X-ray pulses. For example, if you use 290 eV, you can excite specifically carbon atoms. At 500 eV, you can specifically excite oxygen. And then you can do several pulses and watch what's happening in the molecule. So I will talk about several techniques. The first one is using stimulated Raman, what we call TrueCars, and then time-resolved diffraction. And then I will talk about twisted X-ray light, which will connect very nicely with the previous talk. And then I will talk about electron diffraction. And these are all applications in the X-ray. And then I will talk about quantum light and optical cavities. So in ordinary Raman, with optical beams, you go up and down and you create a vibrational coherence. If you do it with an X-ray beam, you go up and down and you create an electronic coherence. The X-ray beams have a broad bandwidth and they can excite coherently valence excitations in the molecule. One feature here is that the effective polarizability is dictated by the bandwidth, and if you have 100 attosecond pulse, it has a 10 eV bandwidth, so you create coherences that are not possible to do otherwise. This is an example of an amino acid cysteine, where if we excite it at the nitrogen, the oxygen, or the sulfur edges, I can get electron and hole wave packets that are localized on the specific atoms. So the idea is to do this, and then after a delay to do it again, and then to watch how these wave packets evolve. Right. So the process I would like to discuss is conical intersections. When you have excited state of molecules, they have several electronic states, and there are regions in configuration space where two electronic states become degenerate. Under these conditions, the electronic and the vibrational frequencies are comparable, which means that their motions are strongly correlated. You cannot use the adiabatic Born-Oppenheimer approximation. And what happens is that in these regimes, this is where most of the interesting photochemistry and photophysics occur, because when the electronic and the vibrations are strongly coupled, you get a rapid and efficient energy transfer between the degrees of freedom, and that opens up many possibilities. So I would like to tell you about a technique that we call true cars. If you look at a cars signal, you usually have an excitation that creates a coherence and then another pulse that detects it. In the true cars, we let the coherence evolve intrinsically in the molecule and we just probe it. So this signal will be zero unless there is a coherence. This signal will be zero unless there is a coherence in the molecule. And what we are building upon, the fact that if I excite the molecule here and I let it evolve, coherence is only created at the conical intersection when the electronic states are strongly coupled. And so this is a selective probe of the conical intersections. You know, it is well known that conical intersections are important and they have been predicted theoretically, but there is no clear evidence, background-free evidence for the conical intersection. So this technique that I'm showing you can do that. Another thing is that we are using stimulated Raman because valence excitations are much more interesting than core excitations for chemistry, for example. And if we do a stimulated Raman with the X-ray beams, we can excite valence excitations and we can excite them in the vicinity of a selected atom. So this is the uracil, which is an important RNA base. And what happens is you excite it from the ground state S0 to the first and to the second excited state. And we use these two coordinates to describe the photophysics of the molecule. And so I excite it to S2, and then due to the conical intersection, it relaxes to S1, and then eventually to S0. And what you can see here is a wave packet that we excite. Right, we excite the wave packet in S2, and then it crosses over to S1 and then to S0. And this is the true car signal. It's a function of frequency and time delay. And what you see here is a pattern of gain and loss events that oscillates with the coherence time scale of the wave packet. So this is the predicted true cars signal, and it carries information about the superposition state and the coherence. So yeah, so this is a summary. I have the polarizability as a function of time. I have the kinetics of the states, and then this is the actual signal. Now, it's possible to plot it using a Wigner transform of a frog signal, and then what you see here is basically a distribution of frequencies, how it evolves with time. So when you go across the conical intersection, you get many frequencies, low frequencies that are participating. And this picture of basically wave packets of vibronic coherences as a function of time, that's the indication of the conical intersection. You see that the signal vanishes when I'm away from the conical intersection. It only exists during the conical intersection. If I use a shorter pulse, 20 femtosecond, I have a broader bandwidth of observation. So this stimulated Raman X-ray technique allows us to probe the conical intersections in an unambiguous way, which means this signal will be zero unless there is the optical coherence. Now, these coherences are robust even if you have many, many degrees of freedom. These are examples of two complexes that appear in light harvesting, where we use not only two coordinates, but the complete nuclear coordinates of the molecule using some semi-classical propagations. And what you see here is that these are the signals for these two type of molecules. You see that the signal does survive, and it's robust to many, many vibrational modes. All right. Now, as a rule, any interesting signal is weak. That's usually the case. And so these signals are relatively weak, and it's possible to enhance them, for example, by shaping the pump pulse. You can shape it and require that there will be a large coherence at a certain time, like say 100 femtoseconds after the initial excitation, and you see that we can get an optimized pulse that gets the transition to occur at 100 femtoseconds. And then we can shift it at will. So we can do a coherent control schemes in order to enhance the signals. Now let's turn to coherences in diffraction. Diffraction, usually you don't think about coherences, you think about basically time-dependent charge density. However, if you do time-resolved diffraction, you get many contributions coming from populations, which means charge density, and also from coherences. And the stimulated Raman gives you a temporal and spectral picture of the conical intersection. The diffraction also gives it to you in space, so you can see how the coherence looks in space. So the experiment is that we excite optically, we let the molecule evolve, and then we can come with an X-ray and probe the scattering. So so there are many contributions coming from ground state populations, excited state populations and coherences, and also from vibronic coherences. And all of these add up to get the signal. And what's interesting for us is the contribution of coherences. This is an important molecule, azobenzene, that can have two configurations known as trans and cis. And this molecule is used in switching of devices, and also in triggering different molecular processes. So basically, if we look at this isomerization of the molecule, we excite a nuclear wave packet, and then it crosses over from the cis to the trans, and this is how this process occurs. And now we would like to see how we can observe the coherences by doing this X-ray signal. So let me show you the picture. These are the different contributions to the signal This one on the bottom right is the one coming from coherences. The rest are contributions of different populations and charge densities. And if you watch, yes, you see, this is the picture. This is the picture that will be obtained coming from the coherences. It is much richer than the population parts, but it is about 2,000 times weaker. So one should try to enhance the signal in order to get stronger populations. And this is another view of these signals, and these are the contributions of the coherences. I would like to mention, if you look at it in Q space, the coherences give you a stronger contribution in high Q, because the coherence is well localized in space, and it gives you a signal at high wave vectors. So that's one way to discriminate and to observe it in a clear way. Again, it's possible to enhance the signal by adding more pulses. For example, if we add an infrared pulse during the crossing to the conical intersection, it can induce a stronger signal that has to do with coherences. So this is my a second example where we view coherences through a diffraction.
I'm very sorry, very sorry. Your laptop shows as it has 1% of charge. A few minutes ago, it was 3%. I'm afraid it's just discharging.
Sorry, I didn't get your question. Please repeat. Yeah.
Could you
Your laptop, 1% electricity, 1% battery.
Your laptop battery is getting empty. Please connect it to.
Just a minute. I thought I was charging. Just a minute.
All right, seems quite a pity. Obviously,
Looks like it was discharged.
it's not discharged. Anton, thanks a lot for this hint, but maybe it was too late. I guess we could wait a little bit. Maybe Charles manages to put the laptop up. Olga, how shall we proceed? How long shall we wait? I mean, I could show some slides as an entertainment in the meantime, but I don't know when Charles is going to show up again.
Sorry, Rennie, I just realized that I had my microphone muted.
Okay.
So what I'm thinking is that we should still wait for Shoal. Hopefully he can reconnect. It's his time anyway.
Yeah, it's a pity.
Yes, I sent him emails that we are waiting for him and hope for reconnection. At least we know what is the problem.
Yeah.
Otherwise, he would disappear mysteriously.
Yeah. The problem, I think, was that he couldn't find his cable immediately.
Yes, I think this is the case, yes. Yeah.
right, Olga, I would say we wait until 3:30 UTC, and if he doesn't show up, then we close the session, right?
Maybe yes. It's
unfortunate, but I'm sure we will hear Shaul another time, another conference, or maybe next year.
Well, we can try, especially if it will be in some place so much technology is involved for him.
Yeah. Well, all right. I'm terribly sorry for all those who have waited. We lost the second half of a pretty nice and interesting talk, but obviously the technical problems that occurred couldn't be solved. So I thank you for your patience, and thanks to Carlos for his talk, which was really a highlight, and the first half. Thanks to Shaul, I will send him an email. So thanks for staying here, and I close the session.
I think that Shaul just connected, right?
Oh, connected?
Oh, wow.
Oh, then let's wait. Let's give, let's say 10-15 minutes, 10 minutes for talk, 5 minutes for question, if any.
Yeah.
He's in the list, at least in the...
Yes, I see him now.
Sure, can you hear us?
Yes, yes.
Okay,
right.
Great.
Oh, good, you made it. So maybe you, I'm sorry, we have all been waiting now. Maybe you make an ultra short finish of your talk and a few questions to discuss.
Yes, I didn't realize that I was disconnected at the end. I'm sorry. So let me summarize. What I tried to show you is that we can use a novel type of light to probe coherences and through them to learn about elementary processes in molecules. So in the first part, I talked about ultra-short X-ray pulses that can measure coherences between electronic states, and they can be used to probe what is called conical intersections, which means when you have regions in phase space where electron and nuclear frequencies are comparable, and then you can get efficient energy transfer between the two. And the X-ray pulses can probe these coherences unambiguously. Then I showed you the possibility of using orbital angular momentum light in order to take diffraction signals, and by subtracting L and minus L, we can eliminate populations and get the coherences, which is a great advantage of using the orbital angular momentum light. After that, I talked about using quantum light, in particular entangled photons, in order to obtain high temporal and spectral resolution that is not possible with classical light, because the time and the frequency are not Fourier conjugates, and you can get a high resolution of both. And in the last part of the talk, I talked about putting molecules in cavities, and you have molecules that normally do not interact, but if you put them in a cavity, they interact via the cavity mode, and then you can get induce and control a charge transfer that is not possible otherwise. So this is a brief summary of what I was trying to say, and I'm sorry for the problem with the communication. Yes.
Sorry, I was muted. Thank you so much for your summary, and I'm really sorry that this happened, because we were enjoying your talk. Other questions?
Yes, please.
Yes, Vitaly, please.
It's really fascinating that now you can have a time-resolved information about this conical intersection and non-adiabatic level crossing in a single molecule. But my question is, obviously, this non-adiabatic level crossing is not as simple as just Landau-Zinner standard model. It should be very sensitive to how this how these parameters changing in time and how this intersection happens. So the result should be very sensitive. What about the robustness of this kind of the spectroscopy?
Okay, I showed, I don't know if this part of my talk showed up, that we have done some exact calculations for a molecule with 2 vibrational degrees of freedom, and then we did semi-classical calculations for much larger molecules with 30 or 40 vibrational degrees of freedom, and we showed that the signal was robust, which means this time-resolved coherences survived the fact that there are decoherence effects due to many coordinates. So I would say, we have evidence that the signal is robust and can be detected even if large molecules with many nuclear degrees of freedom.
Yes, that's very nice. Thank you.
Thank you. Olga, you have a question?
Sure, these are very interesting results, but in terms of experimental implementation,
Yes.
if there are some experiments which are planned, because my always concern, about this noisy nature of X-rays, but I remember you mentioned one that it's even good, there is opportunity to use it for advantage. So how does it work?
Yes, I skipped that part in this talk, but in general, you can use actually the stochasticity of the X-ray pulses to get new information. And the reason is, when you have stochastic pulses, you accumulate a huge database of many signals with different realizations of the pulse. And now you can use this database to, at the data processing stage, to create new types of correlation functions. For example, you can do a correlation between the signal and the incoming pulse. And this is a new information that you cannot get if the pulses were coherent. So at the data processing stage, you can use the fact that you have an ensemble of a large number of data in order to get new signals. And we have demonstrated that you can get this true cars signal, which looks at the stimulated Raman, and you can get it very nicely, even if you have a stochastic pulse. Now, several groups are planning to do these experiments in SLAC, and there are 2 beam proposals that are now being considered, and hopefully these signals will be reported maybe in the next year or so. Yeah.
I see. Thank you.
Thank you very much. Do we have more questions? All right, this is not the case. Then let's thank Charles for coming back to us and answering the question, giving this interesting summary. And also thank both speakers. These were really nice talks, and thanks all for attending. Bye-bye.
Bye.
Thank you, Reinhard, for chairing this session, and thank you to our speakers and everybody who stayed with us, waiting for continuation of Charles' talk. And let me just remind you that our seminar is not over. We still have 2 interesting sessions, and everybody is welcome. Seminar 1.
All right. Thank you,
Bye.
Olga.
See you.
Thank you.
Here,
Bye-bye.
Thank you. Bye.
Goodbye.